Good morning. Am I audible? Please check audio and video. Let's start the new chapter, chapter 2, that is crystallography. Chapter 2. Crystallography. Graphy word is related with the study of something. So here crystallography means study of crystals. So what we are wanting to study in the crystal? Obviously how the atoms are arranged in the crystal, that we are wanting to study. These atomic arrangement may lead to any kind of internal or external symmetry, and those symmetries may lead to properties of the material. So basically we are wanting to investigate how the atoms are arranged in the crystal. Is there any symmetry possessed by the atomic arrangement? And because of this symmetry, what are the characters exhibited by the material? That is the ultimate aim to study in the crystallography. But the biggest problem is just merely by observing any crystal. किसी crystal को just देख करके हम ये नहीं कह सकते कि what is the property of this material. We cannot say about the property of this material because our eyes are not capable to watch atomic level particles, atoms, things of the atomic size. So we must do some experiment. We must proceed for some experiment. So in fact we go for X-ray diffraction. What we do? We take a sample of the material regarding which we are wanting to study, and a beam of X-ray is targeted on this sample. How this beam is reflected or refracted, that is recorded on a photographic film. And by observing the pattern on the photographic film, we can study, we can have sufficient information about the internal arrangement of atoms in the material. This technique is known as X-ray diffraction technique. So by using X-ray diffraction technique, we can study the crystal structure. Now the biggest problem is, but not problem, basically X-rays we are using, but along with the X-rays we can use other rays also, like Rutherford used alpha rays. Similarly, in some of the experiment, neutron beams are used to study some magnetic characters, and in some of the cases we use electron beam also. So different kind of rays can be used to study the properties of materials. In fact, the best way is X-ray. Why the best way is X-ray? The reason behind is the method using X-ray is very cheaper one. So it is very cost effective. X-rays can be easily produced and they are cost effective, and as well as they are easy to handle. आप देखें, if ever you have gone for the X-ray in hospital, so you may have seen it could be easily done. So it is easily handleable and things can be easily done by using X-rays. So X-ray technique become popular, although we can use several other types of rays also to study the pattern, atomic arrangement profile in the material. So before I proceed to discuss this chapter, let us first write this definition and then we would be proceeding. This chapter is very important. If you see last 6 years paper from 2017 to 2022, you will find more or less, except 1 year or 2 year, every year there are questions, and few years questions are in large number, 2-3 questions from a single topic. So it is a very important chapter. You need to put sufficient focus on this chapter in order to understand it properly. So let's go for this chapter, crystallography. And before that, please note down the definition of crystallography. मैं dictate कर रहा हूँ, please keep on writing. Again someone has written, please explain in Hindi also. Sir, dear you will not understand my problem, right? I told you the method, I told you my limitations, still you people are not able to convince, then what can I do? मैंने आपको अपनी सारी समस्या बताई कि मुझे जिस मोड में पढ़ाने के लिए कहा गया, इट इज़ अ रिकॉर्डेड मीडियम, इट इज़ नॉट अ क्लास, राइट? सो जिस भी मोड में मुझे पढ़ाने के लिए कहा गया है, आई वुड बी टीचिंग इन दैट मोड ओनली. आई कैन नॉट डिसाइड माई सेल्फ कि इन वॉट मोड आई हैव टू टीच, राइट? Please note down the definition of crystallography. Crystallography is a branch of science. Crystallography is a branch of science. Crystallography is a branch of science in which the internal structure of crystals, comma, the properties of crystalline materials, the properties of crystalline materials and internal and external symmetries possessed by crystalline solids, internal and external symmetries possessed by crystalline solids are studied. As I told you, this crystallography is done with the help of X-rays, so you can note that point also. Crystallographic methods depend. Crystallographic methods depend on the analysis of diffraction pattern of a sample, diffraction pattern of a sample, diffraction pattern of a sample of material targeted by a beam of X-rays, diffraction pattern of a sample of material targeted by a beam of X-rays, neutrons or electrons, etc. Neutrons or electrons, etc. This is basically definition of crystallography and how does the crystallography is done, right? Some of you may have contacted to the management. What was their response regarding this Hindi and English? The simple solution is the batches should be separated. Hindi batch should be separated, English batch should be separated. Then I am capable of speaking in both of the languages. I can teach in English and I can teach in Hindi, both. I can understand your problem, but I am also bound by the rules. So, this is the definition of crystallography. Crystallography is a branch of science in which the internal structure of crystals, the properties of crystalline materials, and internal and external symmetries possessed by crystalline solids are studied. Crystallographic methods depend on the analysis of diffraction pattern of a sample of material targeted by a beam of X-rays, neutrons, electrons, etc. Right. Now you see, before we proceed to study the crystallography, let me discuss what are the types of solids. Solids can be broadly classified as crystalline solid, crystalline solids. Crystalline solids are those solids in which atomic arrangement is regular and perfect. Atoms are arranged in perfect and periodic arrangement. Atomic arrangement is perfect and regular. Leave it. Crystalline solids are those in which atoms are arranged in perfect, regular and periodic manner. So, they follow a long range order of periodicity. Long range order of periodicity means up to so many atoms the periodic order is followed. Thousands, millions, lakhs of atoms follow the periodic order. So, you can write it ki atoms are packed in regular and periodic manner Long range order of periodicity, long range order of periodicity is followed by atomic arrangement. Long range of periodicity is followed by atomic arrangement. Order of periodicity is followed by atomic arrangement. So, those crystals in which atoms are arranged in a systematic and periodic way, they are known as crystalline solids. What is the definition of non-crystalline solid? Let us have a look. Non-crystalline solid. Non-crystalline solids here atomic arrangement is not perfect, it is not regular, it is not periodic. Atoms are arranged in random manner, any atom, anywhere. There is no periodic pattern followed by the atomic arrangement. So, atoms are packed in random manner. Atoms are packed in random manner. Packed in random manner. Long range of order of periodicity. Long range order of periodicity of atomic arrangement is missing is missing in these solids. Long range of order of periodicity is missing in these solids. ये बनाएं और इस बात को लिखें, फिर आगे चलते हैं. अरे बाप रे. Arun Vasisht ji, it's not only your batch. In this batch, I think so many batches has been merged, and that is the reason they may have informed me according. मूड खराब हो जाता, हमसे कुछ और बोलते हैं और फैकल्टी से कुछ और बोलते हैं. मे बी अर्पित जी, मूड नहीं खराब करना चाहिए, गिव अप नहीं करना चाहिए. Suraj Kumar Meena ji, you are teaching me how to teach in this batch. I am telling you I don't have any problem in teaching in Hindi. I have been told to teach in English because in this batch there are English batch students also. You are not only the English batch student. You are telling me to teach like this, like that. अरे बेटा 12 साल से यही कर रहा हूँ, मुझे पता है किस बैच में कैसे क्या पढ़ाना होता है. बट जब मैंने बताया कि मुझे जिस तरह से पढ़ाने के लिए बोला गया वैसे ही पढ़ाएंगे ना. I don't think we need to contact management for these little things. Okay. खैर चलिए, मीना जी की अपनी राय है. Atoms are packed in random manner. Long range order of periodicity of atomic arrangement is missing. Means atoms are not packed in a periodic way. They are haphazardly packed. Now if you see, if you put X-ray in these materials, so since the atoms are arranged in a periodic manner, so you will get a very well defined diffraction pattern. As the atoms are arranged in same way, you would be getting the diffraction pattern. And that's why in the later sections I will be telling you that some solids are making cubic crystal structure, some are making hexagonal crystal structure. So some well defined geometrical arrangement would be observed in the atomic filling. So you can say that in these materials we get well defined X-ray diffraction pattern. Well defined X-ray diffraction pattern is observed. Pattern is observed. Well defined diffraction, well defined X-ray diffraction pattern is observed. But here you see, my dear friend, if atoms are arranged in random manner, you cannot get any well defined pattern. Because if atomic arrangement is random, then X-ray diffraction would be random and you will get a random pattern, haphazard pattern. So by watching that random pattern, you cannot get any information regarding the crystal properties. So we can say that we do not get well defined diffraction pattern. It means we do not get any kind of well defined geometrical shape in the arrangement of atoms. And that's why these materials are sometimes also called amorphous material. Amorph word means, actually the morph word is taken from shape. It means shape, and A is used for not. So since these materials do not exhibit any well defined diffraction pattern, very well defined geometrical shape in atomic arrangement, that's why sometimes they are also known as amorphous solid. These are also known as amorphous solid or amorphous material. So you can write, these materials do not exhibit well defined diffraction pattern. these materials do not exhibit well defined diffraction pattern. These materials has random atomic structure just like liquid. So sometimes they are also called as supercooled liquids. The only difference is liquids can flow and these cannot flow. So it seems that a liquid has been frozen. That's why sometimes the name is given as supercooled liquid. Supercooled liquid, right? Sometimes these are known as pseudo-solid because their atomic arrangement is similarly to liquid. So sometimes you can say them like these are not actual solids, so they are pseudo-solids. So please write all these names. हिमेश सिंह जी, जितना प्लीज़ आप मुझसे करते हैं मुझे उतना ही मुझे दुख होता है। सूरज जी, ऐसा कुछ भी कमेंट ना करें कि मुझे आपको ब्लॉक करना पड़े। For you it may be little thing. Repeating the same thing in 2 languages, it means double the time. Will you allow the double the time to teach the same subject, 60 hours, 70 hours? Will the management will allow to teach the same subject for 60 to 70 hours? Why are you attending this class? It's a small thing. You feel, you talk with the students who belong from the southern part, they are not able to follow even a single word in Hindi. If I speak in Hindi, वो फॉलो कर पाएंगे? तुमको लगता है कि सिर्फ तुम्हारा बैच है, तो सिर्फ तुम्हारा बैच नहीं है, इसमें इंग्लिश वाले स्टूडेंट्स भी हैं, इंग्लिश बैच के स्टूडेंट हैं, इंग्लिश ओनली बैच, इट्स नॉट इंग्लिश, तुम ही इंग्लिश हो। And don't do all these kind of absurdities. I will block, and if I block, then no one will allow you to attend this class. Better you leave this class. You don't have even basic knowledge of the language, and you are teaching me how to teach. You have done engineering and you don't know even a single word. You are not able to follow, and you tell me after such a long experience that I should be not able to handle this and that. Atoms are packed in random manner. Long range order of periodicity of atomic arrangement is missing in these solids. These materials do not exhibit well defined diffraction pattern. Because the atomic arrangement is not well defined, so diffraction pattern will also not be well defined. Next, suppose I give you a volume and I say that in this volume you have to arrange things in a systematic and periodic way. This is the one method, and the other method is you take the same volume and fill this randomly. So obviously when things are randomly put in a given volume, then lots of space in the given volume will remain empty. So, mass per unit volume will be less. Whereas, if you fill things in the systematic and periodic way, then the volume will be occupied in the best possible manner. And if the volume is occupied by the best possible manner, then mass per unit volume would be high. So, because of the systematic filling in the first case, the given volume can be utilized in the best possible manner, and in the given volume large number of atoms can be packed. So, mass per unit volume would be high. Whereas, because of the random filling of the atoms, lots of space may remain unutilized. So, mass per unit volume cannot be that much high as in the crystallographic case. And this is the reason crystalline solids generally exhibit high density, whereas non-crystalline solids exhibit low density. So, it is high density and it is low density. It is high density and it is low density. Next, next one is since periodic arrangement of atom is being followed, it means after each interval, after certain group of atoms, all the same atomic arrangement would be repeated. It means throughout the material you would be getting identical kind of bonding. Now, let us suppose you start to increase the temperature and you provide sufficient thermal energy to break the bond. Since all the atoms are following a periodic order of the arrangement, so all the bonds are identical, and hence at a given temperature all these bonds will break simultaneously. And if all the bonds break simultaneously, then at a single temperature the whole material will melt. So, if it is a perfect crystalline structure, then at the every place you will have equal bond strength, and hence at the single temperature whole material will melt down. So, you will get a single melting temperature, sharp melting temperature. It may be high or low, that is a different thing, but at a particular temperature whole material will melt down. Whereas, if we talk about non-crystalline solids, so in case of non-crystalline solids, since there is no periodic arrangement, so some bonds can be very strong and some can be very weaker. So, when you start increasing the temperature, the weaker one will first broken and the stronger one will be broken later on. And this way the material will not melt at a single temperature, instead that will melt over the range of temperature. As much as non-periodicity would be there in the atomic arrangement, that much would be the range over which the material is melting. And if it is a perfect periodic arrangement, then the material would be melting at a constant temperature, at a particular temperature. So, you can write this point also. These materials, these are having sharp melting point, These are having sharp melting point. That is, whole material melts at a single temperature. Whole material melts at a single temperature. Here, it melts over the range of temperature. It melts over the range of temperature. It will not melt at a single temperature, instead it will melt over the range of temperature. Please note down these differences. I feel pity on you, Mr. Meena. I have not to say anything regarding your comment. You are writing that I am not going to apologize with you. Taking knowledge from someone is not just you are attending someone's lecture and then you will understand everything. There should be a mutual relationship between the two members. Then only the knowledge can be transferred from one person to the another person. Take my guarantee, you attend the whole lecture, but still you will not be able to follow, able to perform good in this particular subject, because you are attending this lecture not considering me as a teacher. You are attending this lecture considering me as a service provider. And that is the reason you will not be able to get even a single thing in this subject, right? So I don't need any kind of apology from your side. I feel pity for you. You are not the first student whom I am teaching, right? I have taught roughly around more than 2 lakh students. Thousands of my students are in various kind of top level services. First you reach to that level, then you talk. Your apology is not required. You are not a significant person for me. But your behavior as a teacher and as a student, we should understand each other's limitations. But you do not have capability to understand the things. It melts over the range of temperature. These are having sharp melting point. Whole material melts at a single temperature. आपको लगता है कि सिर्फ आपका बैच है, मैंने क्या बताया कि इसमें इंग्लिश और हिंदी दोनों बैच हैं, ठीक? तो यदि मैं हिंदी में बोलता हूं तो इंग्लिश बैच वालों को प्रॉब्लम होती है, मैं इंग्लिश में बोलता हूं तो हिंदी बैच वालों को प्रॉब्लम होती है. एंड यू आर सेइंग दैट कि इट इज अ स्मॉल थिंग, आई शुड मैनेज. Now, most of the natural crystal, most of the solids which naturally occur, some of them may be found in the crystalline form and some of them may be found in amorphous form. But we can also make a crystal and non-crystal from a material. Suppose you take a piece of iron and you go to the blacksmith shop and you say to him, sir, please make a knife from this iron. So he will not immediately start processing it. He will not immediately start performing operation on it. Instead, he will put into a furnace and he will start raising the temperature of this material. When the temperature is raised, the material starts converting from solid to liquid. So it almost goes into the molten state. Almost, not exactly, but it almost goes into the molten state. Now he performs operation on this material and then he tries to cool it again. So he keeps some water and he tries to put that metal piece into that water. So when he is putting into water, actually he is lowering down the temperature. So again he is wanting to make a crystal from that molten state. This process of again getting crystalline state is known as recrystallization. And during recrystallization process, the rate of cooling decides the transformation of the material. If we cool slowly, then atoms will get sufficient time to arrange themselves properly. And if they get sufficient time to arrange themselves properly, then you will be getting crystal structure, because perfect arrangement means crystal structure. But suppose you rapidly cool it. When you rapidly cool it, then because of the rapid cooling, atoms do not get sufficient time, and if they do not get sufficient time, then they get frozen up in their random atomic state, and if they get frozen up in the random atomic stage, then you cannot get crystal. Instead, you get non-crystalline material. So the point is how we are cooling a material from its molten state, that will also decide whether we will be forming a crystal or we would be forming a non-crystalline material. For example, let us talk about a material, that is sand. It is very important material from engineering point of view. Suppose you increase the temperature of sand and it goes into the molten state. SiO2, it goes into the molten state. When it goes into the molten state, if you slowly cool it, slow cooling process, my friends from mechanical engineer would be available here. They may be knowing that is known as annealing. Very slowly we are cooling. We are cooling 10 degrees centigrade or less than that per hour. So if we slowly cool, atoms will get sufficient time and they will make a material, that is quartz. Quartz is a single crystal material. So we are getting crystalline solid. Suppose same material we are rapidly cooling. Let us rapidly cool the same material. So if we are rapidly cooling the same material, it will become glass. And glass is amorphous material. Now since we are rapidly cooling, so atoms are not getting sufficient time to arrange themselves in systematic way, so we cannot get the crystalline solid. Instead we are getting the amorphous solid. So please note down this example. This is very important example. Yes, Himesh, I am explaining it. Just write down, I will explain it again. Achilles is asking, sir, which type of bonds these solids have? Dear, any kind of bond can be. There can be ionic bonded solid like NaCl. There can NaCl is also solid and that is also a crystal. There can be metallic solids like iron, copper, they are also a solids, right? There can be covalent solids like diamond. So any kind of primary bonding would be available over there. Yes, Ritvik. Rapid cooling means quenching. Written? Shall we go ahead? Right. Some of the people were not able to understand how we are getting single melting temperature. Actually, If you have periodic and systematic arrangement throughout the entire crystal, then interatomic spacing between each atoms will remain constant. Throughout you will have same interatomic spacing. Same interatomic spacing means almost all the bonds are of same strength. Because interatomic spacing means what? Distance between the two atoms, and this distance between two atoms depend upon the F net, and F net is what? Bond. So this is basically the bond strength. Same interatomic spacing means all the bonds are of the same strength. Suppose you increase the temperature, and let us suppose 1500 kilojoule per mole is required to break any bond. So if all the bonds are of same strength, then as soon as your temperature supplies this energy, all these bonds will be broken simultaneously. And if all the bonds are broken simultaneously, then your material will melt down. Because bonds are broken, so atoms will go away, and if they go away, then solid will does not retain solid structure, it will convert into the liquid structure, so it will become liquid. This thing happens in the crystals. In the non-crystalline materials, you can have variable interatomic spacing. Some atoms can be very close and some atoms can be far away. So if the atoms are very close, then interatomic spacing is less and hence bond is strong. But if atoms are far away, then interatomic spacing is large, and if interatomic spacing is large, then bond is weak, right? So suppose I start to increase the temperature, then thermal energy will start to increase. So the bonds which are weaker relatively, not exactly but relatively, let us suppose it requires 1500 kilojoules, so it would be required 1490 kilojoule, 1480 kilojoule. So this bond will first break. So at this point the material will melt, but it is still there. It has not broken. So here the material is solid. So now material is not completely solid, completely liquid. It is mixture of solid and liquid. So make it completely liquid, you need to increase further temperature. So when the further temperature is increased, this bond will also be broken and the entire material will become liquid. So here the melting will start as soon as the weakest bond would be broken, and it will keep on till the strongest bond is broken. And this way the entire solid will take a range of temperature to convert into the liquid. That's why I am telling that these materials melt over the range of temperature, whereas these materials, because of the identical arrangement of atoms, same strength of bond through the entire crystal, melt at a particular temperature, means they have sharp melting point. So hope this is clear to everyone. Now the second thing is कि someone asked why we say amorphous materials supercooled liquids. Actually liquids do not have any periodic arrangement of atoms. Liquids have random arrangement of atoms, and these non-crystalline solids also having random arrangement of atoms. So if you see from atomic arrangement perspective, then amorphous solid and supercooled liquids both are identical. The only amorphous solid and liquids both are identical. The only difference is liquid can flow but solid cannot flow. So it seems that if random atomically arranged liquid is frozen, then it will convert into the solid. That's why it is known as supercooled liquid. You take the random atomic structure, the liquid state, and freeze it rapidly, freeze it up to the melting point, then whatever structure you are getting, that is supercooled liquid, yeah, amorphous solid. That is the reason behind this name. Someone asked this rapid cooling process is known as, quenching, right? But not required to be named. So mechanical people may be knowing, not required for any other branch. Okay, next we can go for. Yes, at high temperature, iron can be ashes. It can be converted easily into the desired shape. Quartz is crystalline material. आगे चलते हैं नेक्स्ट. So this way we have discussed the difference between crystal and non-crystal. In this chapter we are concerned up to the crystals. For non-crystals we will be reading the separate chapter that is known as polymers. So that would be studied later on. First of all, let us focus on the crystalline material. So go to the next heading, that is crystalline solids. Crystalline solids can be divided in two types. First one is single crystal material. Single crystal material. Here, throughout the entirety of specimen, entirety means in whole specimen without any interruption from this point to this point, atoms are arranged in single orientation. All the atoms are arranged in a particular direction. Let us suppose with respect to x-axis at 30 degree, then all the atoms are at 30 degree with respect to x-axis. So they have single orientation. All of them are arranged in a single orientation throughout the entirety of the specimen. यानी पूरे के पूरे मटेरियल में all the atoms are arranged in a single orientation. For example, if you ever has gone to cinema, movie theater, then everyone has eyes towards the screen. So each of the person is in the single orientation. So the structure which they form, if every person can be considered like an atom, so that structure will be known as single crystalline arrangement. So in a single crystal material, without any interruption, without any discontinuity, all the atoms are arranged in single orientation. Means I will be teaching you after a few moments the concept of unit cell. So all the unit cells interlock in the same direction. They have the same orientation. That is the definition of the single crystal material. Whereas in polycrystalline material, what happens? There are several small regions. There are several small regions. And in a particular region, all the atoms are arranged in single orientation. All the atoms are arranged in single orientation. But the arrangement of atoms differ from one region to another region. But the arrangement of atoms differ from one region to another region. So in a particular region, all the atoms are arranged in a direction, but the direction of arrangement of atoms is different. Right? So doesn't it seem that this is a single crystal, this is a single crystal, this is a single crystal, this is a single crystal? So entire material has been made with the combination of so many crystals. That's why the name is polycrystal. Poly means many, and crystal is something where the atomic arrangement is systematic and periodic. So it seems that this entire crystal is made of so many single crystals, and that's why it is known as polycrystalline material. A particular region in which all the atoms are arranged in single orientation, that region is known as grain. That region is known as grain. And the boundary which is separating two grains, this boundary, that is known as grain boundary. The boundary which is separating two grains, that is known as grain boundary. Basically, grain boundary is a place where atomic arrangement is mismatched. Before this, atoms are in a particular orientation. Let us suppose with respect to x-axis at 30 degree. But after this, their orientation is different. Let us suppose with respect to x-axis 32 degree, some different arrangement. So in polycrystalline materials, there are large number of grains. In a particular grain, all the atoms are arranged in single orientation, but the orientation of atoms differ from grain to grain. Because of this reason, polycrystalline materials will be stronger. Why? Let us suppose in the single crystal I apply a force like this. So this force is experienced by these atoms and they are pushed towards this side. So these atoms will be dislocated from their position, and as they dislocated, their bond would be broken and material will break down into two pieces. But here you see, my dear friend, as soon as I apply a force, so atoms will try to go this side, but the atomic arrangement is different at this side of the boundary than this side. So the atoms which are in this grain, they will push back to this atom. So it seems that grain boundary is restricting the movement of atomic dislocation. And if atomic dislocation become difficult, then you have to further apply the force to dislocate them. And hence material has capability to sustain more applied load. Hence its strength is high. So in the polycrystalline materials, there are a large number of grains and each grain has different orientation, because of which grain boundaries obstruct the movement of dislocation, and this obstruction results into the increased strength of the material. So generally polycrystalline materials are stronger than the single crystal one. And this strong character is coming because of the grain boundaries. And that is the reason, if my friends from mechanical engineering are there, for remaining engineering it's not required, but for mechanical engineering, if you recall, you may be taught in your subjects that to increase the fatigue strength, you need to use fine grain materials. Fine grain materials means there should be large number of grains inside the materials. If there are large number of grains inside the material, it means large number of grain boundaries, and these grain boundaries obstruct the movement of dislocation and hence the strength would be higher. So increase the strength of a component, you would be selecting a fine grain material. Other branches के लिए जरूरत नहीं जो बोला, forget about it. So polycrystalline materials में if you see, throughout the entirety of specimen there is no single orientation. The single orientation of atoms is from here to here, then an interruption takes place, and then here to here again the different orientation. So these materials does not have single orientation. It means all the unit cells cannot be locked in the same direction, whereas the previous one, they have the single orientation, all the unit cells are locked in a single direction. So let us first write this. Most of the natural crystals exist in polycrystalline form. Most of the natural crystals are found in this form, but there are some which found in single crystal form also, like sugar, NaCl, quartz. These are the material, diamond, these are the materials which are found in single crystal form. Remaining iron, silicon, calcium, chromium, lithium, potassium, all these are found in the polycrystalline form. So most of the natural crystals are found in polycrystalline form, but there are certain which found in single crystal form also. Please, acha, we can calculate this number of grains. Actually, we cannot see this grain from naked eyes. We need to magnify this structure. In order to magnify this structure, we need to use any microscope. So let us suppose we are 100 times magnifying the structure and then watching this. So at a scale of 100 times magnification, the number of grains per square inch can be given like this. So n is equal to 2 to the power n minus 1, where small n is grain size number. Grain size number. This grain size number is known to us. It is already available with us what is the size of the grain in the material. Then capital N is number of grains per square inch of material, per square inch of material at a magnification of 100 times. at a magnification of 100 times. Please note down this. Nothing like that, Ruchi. It depends upon several other factors. I did not say that temperature of non-crystalline should be greater than crystalline. No, I didn't use this sentence. I said that temperature high and low does not depend only on the one parameter. It depends upon several other factors also. We will be discussing it later on in the further chapters of ceramic, etc. Here I am saying that if it is a crystal, it will melt at a single temperature. But if it is a non-crystal, then it will melt over the range of temperature. That temperature range may be lower than the single temperature, or it may be higher than the single temperature. That we will be discussing in the later on sections, right? Please note down this. I forget to write here polycrystalline मटेरियल. एक्चुअली सुबह सुबह मूड खराब कर दिया ना आप लोगों ने, तो उसकी वजह से things are becoming haphazard. Polycrystalline material, right? And yes, obviously this relation is for polycrystalline, because in single crystalline there is only one grain. So we do not talk about number of grains in the single crystal. The entire crystal is a grain. So if we are talking about number of grain, then obviously it is for polycrystalline material. Yes, Manoj. Grain means the region in which atomic arrangement in a single direction. Then other region, the atomic arrangement direction will change. We would be studying about the directions in the crystal. Those are known as Miller indices. This will be taught in the later sections of this chapter. Sand, quartz and glass में कौन सा crystalline and non crystalline? Quartz is crystal, glass is non-crystal, sand is actually mixture of so many things, so it needs to be purified, right? So sand is not only SiO2, it has several other mixtures also. So we are not talking about a single material when we say sand, because sand is on the earth surface, so it will have several other oxides also. There may be aluminum hydroxide, there may be potassium hydroxide, etc. So from sand we extract SiO2, and that SiO2, if slowly cool, it will get converted into quartz, and quartz is a single crystal material. And if it is rapidly cool, then it is amorphous material, right? Let us please go to the next point. Omkar Sahu answered your question. Achilles, it has several consequences. Basically, this number decides several properties of the material. That's why we counted this number. Shall we go ahead? Right. Let's write these two definitions, and then we will be proceeding further. First one, single crystal material. Single crystal material. For a crystalline solid, when the atomic arrangement is periodic and repeated throughout the entirety of specimen, that is, all the atoms are arranged in a single orientation, then crystal is known as single crystal material. All unit cells interlock in the same way. All unit cells interlock in the same way. All unit cell interlock in the same way. And have same orientation. Orientation means direction. किसने ईसू ने grain is having large number of atoms. So grain ही atom नहीं है. Grain is having large number of atoms in which all the atoms are arranged in a single orientation. Orientation means direction. For a crystalline solid, when the atomic arrangement is periodic and repeated throughout the entirety of a specimen, that is, all the atoms are arranged in single orientation, then crystal is known as single crystal material. All unit cells interlock in the same way and have same orientation. Please note down it. Next, here polycrystalline. It is composed of many small single crystals. It is composed of many small single crystals known as grains, which are separated by well defined grain boundaries, it is composed of many, not may, it is composed of many small single crystals known as grains, which are separated by well defined grain boundaries, In a particular grain, all the atoms are arranged in single orientation, but the orientation of atoms differ from grain to grain, Polycrystalline materials are stronger. Because grain boundaries obstruct the movement of dislocations, Polycrystalline materials are stronger because grain boundaries obstruct the movement of dislocations. Please note down this. सिंगल क्रिस्टलाइन का लास्ट पॉइंट भी देख लीजिए. ऑल यूनिट सेल्स इंटरलॉक in the same way and have same orientation. Yes, Assis, you are 100% correct. Right. No Shreya, it is not the first slide. We have studied so many things. 1 hour से ज़्यादा lecture हो गया है. You can leave 2-3 pages and then go on writing. Note. Most crystalline solids exist in polycrystalline form. But there are some which exist in single crystal form. Such as quartz, diamond, sugar, NaCl, etc. Most crystalline solids exist in polycrystalline form, but there are some which exist in single crystal form. Milu, we are not deriving any relationship in this subject as the exam is objective and limited time has been provided. So, you have to accept the relations as it is. Derivation is not possible in a small course. Right. Next, I want to give some definitions. They are generally asked. So, you can put a heading, a broad heading, some definitions, and please keep on writing one line regarding these definitions. They are generally asked. First definition, anisotropic material. These are the materials which exhibit different property in different direction. Suppose you are wanting to measure electrical conductivity and you measure in this direction, you get X value. Now you change the direction of measurement, and if the value of conductivity changes, it means the material is anisotropic material. So these materials will exhibit direction dependent properties. They have different property in different direction. So such materials will be anisotropic. Generally, if the material has all the atoms in single orientation, then in that direction you will be getting the value of property different as comparison to the other directions. So more the periodic arrangement, higher will be the anisotropy in the material. Anisotropy means material is exhibiting direction dependent property. Suppose you are wanting to measure strength. So let us suppose in longitudinal direction strength is 100 megapascal. So if you measure the strength in some other direction, let us suppose you measure the strength in lateral directions, then if the value of strength is different, it is not 100 megapascal, suppose it is 80 megapascal or some other value, then that material will be known as anisotropic material. There is one more type, that is orthotropic. Orthotropic is subset of anisotropic. If you measure the value of property in 3 mutually perpendicular directions, so if the value of property differ in 3 mutually perpendicular directions, then the material will be known as orthotropic. So orthotropic is subset of anisotropic, means all the orthotropic materials will be anisotropic, but vice versa need not to be true. In anisotropic we can have any direction. Any two direction you measure the property, and if you get the different value for the property, it means it is anisotropic. But for orthotropic you should have perpendicular directions, you should have measured the property in perpendicular directions. So let us first write this definition. So I am telling you, if the material properties depend on the direction of measurement, if the material properties depend on the direction of measurement, that is, material exhibit different value of property, in the different directions, then such materials are known as anisotropic material, Such materials are known as anisotropic material. If the material properties depend on the direction of measurement, that is, material exhibit different value of property in the different directions, then such materials are known as anisotropic material. Means direction dependent properties. In a single word you can write direction dependent properties. Right. Next definition, orthotropic material. If the material exhibit different value of property, if the material exhibit different value of property in three mutually perpendicular directions, if the material exhibit different value of property in three mutually perpendicular directions, then it is known as orthotropic material. Then it is known as orthotropic material. महतोन जी डायमंड की बात करेंगे. डायमंड कार्बन बेस्ड कंपाउंड है and that has sp3 hybridization, so it has several characters unexpected. We will be talking about diamond in the coming chapter, don't worry about that. Suppose you have any material which exhibits same value of property in all direction. Let us suppose you start measuring in different direction. This is a point, right? In this direction you measure the value of property, you get same. In this direction you get the same value. 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 In each direction you are getting the same value for the material property. It means what? Material properties are independent of direction of measurement. Such materials which exhibit direction independent properties, they are known as isotropic material. Although 100% isotropic crystals do not exist in reality, but we assume that for so many polycrystalline materials, we assume that the properties are independent of direction. Right. But in as of now we are not studying material, we are saying that what is the definition of isotropic material. So we say those materials are isotropic where we get the same value of property in all the direction. Let us suppose I am measuring strength. So whether we measure in x-axis, y-axis, z-axis or at any other direction, everywhere if we get the value of strength same, suppose 100 megapascal, then the material will be known as isotropic material. So please note down isotropic material. These are the materials, these are the materials which exhibit direction independent properties, direction independent properties, which exhibit direction independent properties. That is, the value of property is same in each direction. The value of property is same in each direction. These are the materials which exhibit direction independent properties. The value of property is same in each direction. Now, there is one more definition, that is homogeneous material. Let us suppose this is a direction, any direction, and if you measure the value of property at different points in the direction and you get the same value, then material is homogeneous. You need not to be confused in isotropy. Isotropy is in different directions, whereas here we are saying that in a direction, if at the different points you get the same value of property, then material is homogeneous. And if the material properties differ from point to point in space, then the material is non-homogeneous. So you can say that homogeneous material you can define like that: if the material properties do not vary from point to point in space, if the material properties do not vary from point to point in space, along a particular direction, then material is known as homogeneous material. If the material properties do not vary from point to point in space along a particular direction, then the material is known as homogeneous material. बिल्कुल नहीं सेम होगा अनुभव, इट शुड बी डिफरेंट. रोहन, एनाइसोट्रॉपी सिंगल क्रिस्टल में ही एग्जिस्ट करेगी मेनली. यूनिफॉर्म बॉन्ड है लेकिन एक ही डायरेक्शन में, अदर डायरेक्शन में तो डिफर कर जाएगा, और अगर अदर डायरेक्शन में डिफर कर जाएगा देन इट मीन्स व्हाट, वैल्यू ऑफ प्रॉपर्टी विल चेंज. Yes, 100% isotropic materials do not exist in real world. Aditya Sankar Sharma, you are correct. But we assume for so many materials, if there is negligible change in the property in different directions, then we assume them as isotropic. Non-homogeneous material isotropic नहीं हो सकता, क्योंकि अगर पॉइंट टू पॉइंट प्रॉपर्टी चेंज हो रही तो डायरेक्शन टू डायरेक्शन डेफिनेटली चेंज होंगी. There is one more definition. There are certain materials which exhibit different crystal structure at different temperature. For example, iron. At room temperature it has BCC crystal structure, but when you raise the temperature of iron it gets converted into the FCC. It means the crystal structure of iron depends upon the temperature. So if at different temperatures material is exhibiting different crystal structure, then such materials are known as allotropic material, a polymorphic material. There is one more example, carbon. Carbon at room temperature is found in the form of graphite. Graphite has hexagonal crystal structure. But when you increase the temperature of carbon, it gets converted into diamond, and diamond is cubic crystal structure. It means carbon is allotropic, polymorphic. It has different crystal structure at the different temperature. So next definition is allotropic material. These are the material, this is also known as polymorphic, both are same thing, polymorphic material. These are the materials, these are the materials which exhibit different crystal. These are the materials which exhibit different crystal structure at different temperature and pressure. Temperature and pressure are interrelated things. These are the materials which exhibit different crystal structure at different temperature and pressure. Yes, Giri, isotropy we are defining with respect to the direction. So when we are measuring property in different directions, then we would be talking about isotropy, anisotropy. But in a particular direction, if we are measuring the value of property on different points, then we will be talking about homogeneity, whether it is homogeneous or non-homogeneous. That is the only difference. If you talk about in different directions, then isotropy or anisotropy, and if you talk about in a particular direction different points, then it is homogeneous or non-homogeneous. Done? किसी को आइसोट्रॉपी लिखना था, क्विकली डू इट. Orthotropy means you measure the value of property in 3 different directions, but they must be mutually perpendicular. Alok, periodic means what? In a particular direction, all the atoms are arranged in a particular direction, then only they would be following the periodic pattern, let us suppose. So in that direction you would be having higher value of the property, but in the other directions you will not be getting the same value of property. Let us suppose with respect to x-axis all the atoms are arranged. So it is a very much systematic and periodic arrangement. It is a single crystal material. In this material, in the in this direction, let us suppose with respect to x-axis at 30 degree, you will get different value of the property rather than other the directions. That's why I said that the higher the periodicity, more will be the anisotropy. Hari Krishna Prasad, we would be defining several directions, don't worry about that. You know the 3 directions. What are these 3 directions? X, Y and Z. These are what? Mutually perpendicular, right? Apart from this, you can define other direction. This is one more direction. this is one more direction, this is one more direction, this is one more direction, this is one more direction. So there can be infinite directions. Let's go on to some more definitions. Next, बेटा जल्दी लिखा करें, please keep on writing quickly, क्योंकि अगर डिफिनीशन ही लिखते रह गए पूरा दिन तो फिर बहुत लंबा सिलेबस है. सौरभ, ऐसा नहीं है कि बाकी डायरेक्शंस में सेम होगी. सौरभ is saying that in orthotropic except 3 directions, remaining directions में property would be same or different. We are not interested in remaining directions, but if it is differing in 3 mutually perpendicular directions, then it will differ in other directions also. That's why I said that orthotropy is a subset of anisotropy, right? But when we are talking about orthotropy, we do not bother about the other directions. That's why we are saying in the 3 mutually perpendicular direction. But if it differ in 3 mutually perpendicular directions, then it will differ in other directions as well. Next, crystal and lattice. Actually, I am wanting to give clarity what is difference between lattice and crystal. Both of these terms are very interchangeably used. Sometimes you may be saying that people are saying that lattice. Sometimes for the same thing they would be saying crystal. So are these both same or they have any difference? Let us try to investigate it. So I am making a table, and in that table I am trying to compare these two. So let us make a table. At one side of the table I am writing lattice. So let us suppose this is lattice, and at the another side we are writing crystal. Suppose we have 3-dimensional arrangement of points in space. You are having 3D arrangement of points in space. These are the points in space. These I am making 2D points, you can assume it in 3D, right? So it is 2D, but all the crystals are 3D, so assume it in 3D. This 3D periodic arrangement of points in space, this is known as lattice. 3D periodic arrangement of points in space, this will be known as lattice. Let us suppose corresponding to each point you arrange one atom or group of atoms, then what that would be known as? It is atom. With respect to each point you arranged an atom. So we arranged atoms with respect to each point. So one atom, I am showing it by different color. These are the points, lattice, 3D periodic arrangement of points like this. On these points you can arrange either one atom or group of atom. It's your choice whether you arrange one atom or group of atoms, right? So let us suppose I arrange atom. Here can be group of atoms also. Group of atoms means molecules. Suppose NaCl. So you arrange like this. Now this pattern which we get in the three-dimensional space, this is periodic arrangement of atoms in the space. So this periodic arrangement of atoms in the space is known as crystal. This is known as crystal. So what is key difference in the crystal? The key difference in the crystal and lattice is three-dimensional periodic arrangement of points in space. So it is a geometrical concept only. It is not any physical object. It will have only geometrical properties. Geometrical properties, what do I mean? If you connect a 2 point, it will become a vector. If you connect a 3 point, it will become a triangle. These kind of properties it will exhibit. But if each lattice point contain one atom or group of atoms, then it becomes three-dimensional periodic arrangement of atoms. And this three-dimensional periodic arrangement of atoms is known as crystal. So basically lattice plus this atom or group of atom is known as motif या basis. Both of them combinedly make a crystal. So basically lattice plus motif, this is known as crystal. Lattice plus motif or basis, they make crystal. What is motif or basis? It is atom or group of atoms associated with each lattice point. It is atom or group of atoms associated with each lattice point. It is atom or group of atoms associated with each lattice point. Now crystal is a physical object. It will have physical properties, some mass, some density, some volume, some electrical conductivity, some magnetic property. All those things will be exhibited by this material. So we can say that now we can compare it like this. It is a three-dimensional periodic arrangement of points in space. Here it is a three-dimensional periodic arrangement of atoms in space. It is a geometrical concept. It is a geometrical concept, and hence will exhibit geometrical properties, like if you connect 2 points, it will become a line. If you connect 3 points, it will become a triangle. 4 points, a square or rectangle, like that. It is a geometrical concept and hence will exhibit geometrical properties only. It is a physical object. It is a physical object so it will exhibit physical properties such as mass, density, etc. This is the key difference. Basically lattice tells you how to repeat. In a crystal, how to repeat. Basically it is underlying periodicity of atomic arrangement, and motif tells us what to repeat. When you combine these two, then your crystal is formed. How to repeat and what to repeat gives you answer how does your crystal is formed. So please first you note down this, then I will be showing this. Coal is nothing but carbon, and I told you that carbon at high temperature converts into diamond, so that is a allotropic material. But carbon does not convert into gold. आपको किसी ने गलत बता दिया है. It converts only into diamond, not gold. Yes, Ankush, mechanical students may have read this chapter in their material science. So you may skip also, because there you may have studied it in depth. Here we are studying basics of material science, so may not be entering into that much depth. But you people have may read it. Geometrical properties, Nishtha, I mean like what is geometry? Geometry is any shape like triangle, like rectangle, like a square, like a hexagon, anything like that. So geometrical properties means when 2 points are connected, they will become a line. When 3 points are connected, they will become a triangle. So these are the geometrical characters. Arpita, I am telling you, lattice is telling us how to repeat. Suppose you are wanting to make a crystal. So crystal is what? Periodic arrangement of atoms. So periodicity can be in different ways. So how to repeat, how to make the periodic arrangement, this is told us by the lattice. What to repeat? An atom we want to repeat, or group of atoms we want to repeat. Suppose we are wanting to make iron. So iron is stable in the form of atoms. So we would be repeating atoms at each lattice point. But suppose we are wanting to make NaCl, right? So NaCl, Na is not stable. If you will repeat in NaCl, you need Na and Cl both. So with respect to the lattice points, so what is related? Group of atoms are related. So it depends upon the internal arrangement of the atoms, internal property of the material, whether we are wanting to repeat the atoms or we are wanting to repeat group of atoms. That atom or group of atom is known as motif or basis. When you combine these two, means motif is superimposed on each lattice point, then it results into crystal. Crystal is your crystalline material, right? Let us go for the next point. Next definition is lattice translation. Now in our subject we would be interchangeably using both, because crystal is nothing but the atoms at each lattice point. So if crystal is periodic, that periodicity is given by the lattice, so we can use the terms interchangeably. Next definition is lattice translation. Lattice translation. Any vector from one lattice point to another is known as lattice translation. Any vector from one lattice point to another is known as lattice translation. Any vector from one lattice point to another is known as lattice translation. Lattice translation. For example, you see, this is your lattice structure. You connect any 2 points. These 2 points are lattice translation. These 2 points are lattice translation. These 2 points, they are lattice translation. So any vector which is connecting 2 points, that is known as lattice translation. Please note down. Yes, Nandini. Obviously, if the crystal structure will change, then properties will definitely change, because properties are the function of structure. Periodic means well defined arrangement, yes, and it should be repeated throughout the material after certain interval. Pratik. Quickly note down. Next, unit cell. Unit cell. Let us suppose you have lattice. Similarly, you can talk about crystal also, because at each lattice point there would be an atom. So it is nothing but crystal also. It is lattice. This is your lattice, right? So unit cell is a region of space which, when repeated periodically in all the directions, can develop the entire lattice. For example, this square I am taking in 2D. In 3D it will become cube. This is square. It is a region of space. Now if I repeat it through the entire lattice by the lattice translation, then we can develop this whole crystal structure. As you keep on repeating it in all the directions. So this region of space is known as unit cell. Let us suppose at each corner there is an atom. So we can say that smallest group of atoms by repeating which in all the directions periodically we can develop crystal. That smallest group of atom is known as unit cell. Unit cell is not unique thing. There can be several types of unit cell. This can also be a unit cell. You keep on repeating this, you will be getting the crystal like this. So a given lattice can have infinitely many unit cells. It means unit cell is nothing a unique thing. It can be several types of unit cell for a given lattice, for a given material. But we have certain conventions. So we consider atomic arrangement according to those conventions, and that's why we talk about only conventional unit cells like cubic, rhombohedral, hexagonal, all these. Although in a given lattice there is a possibility of infinitely many unit cells, right? So a given lattice can have infinitely many unit cells. A given lattice can have infinitely many unit cells. That is non-uniqueness of unit cell. Non-uniqueness of unit cell. You see here, two types of unit cell I am showing you for the same lattice. It means it is not a unique thing. There can be several types of unit cells for a given lattice. Let us define the unit cell. So a region of space, which can generate the entire lattice, which can generate the entire lattice, crystal, by repetition through lattice translations, by repetition through lattice translations is known as unit cell. Or unit cell is the smallest group of atoms. Unit cell is the smallest group of atoms by repeating which periodically in all the directions, in all the crystallographic directions, entire crystal structure can be developed. Entire crystal structure can be developed. Basically, it is the basic building block of the material. Unit cell is the smallest group of atoms by repeating which periodically in all the crystallographic directions entire crystal lattice can be developed. The entire crystal structure can be developed. Suppose a wall is a crystal. Then that wall is made of small bricks. So a single brick is known as unit cell, and by repeating those bricks you got the wall, right? So same here, a unit cell is nothing but the basic building block. That is the smallest reason by repeating which in all the directions the crystal can be developed. Please note down it. Yes, obviously we are talking about crystalline material. Forget about amorphous now. Everything as of now we are talking about crystal only, Mr. Achilles. Nothing about amorphous. Forget about them as of now. For them we would be studying a separate chapter that is known as polymers. Done? बिल्कुल प्रतीक, you are 100% correct. Now we can have two types of unit cell. One unit cells in which atoms are only at the corners of the unit cell, like this one, these two, here, 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 here. So atoms are only at the corners of the cell. But we can have some other type of unit cell also. Let us suppose there are atoms at the corners as well as some other position also. Here you see one atom can be here, 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 and there is one atom inside the cell. This is also the possibility. So we can have two types of unit cell. One where atoms are located only at the corners of the unit cell. These types of cell where atoms are located only at the corners of the unit cell, they are known as primitive unit cell. They are known as primitive unit cell. But if atoms are located at some other location along with the corners, then it is known as non-primitive unit cell. So let us define primitive and non-primitive unit cell as well. These are primitive unit cell. Primitive unit cell. So primitive unit cells are those unit cells in which atoms are located only at the corners of the unit cell. These are the unit cells. These are the unit cells in which atoms are located only at the only at the corners of the unit cell, only at the corners of the unit cell. These are the unit cells in which atoms are located only at the corners of the unit cell. Here, non-primitive unit cell, non-primitive unit cell. These are the unit cells, these are the unit cells in which atoms are located at, atoms are located at some other positions also, some other positions also along with the corners, along with the corners. Atoms are located at some other positions also along with the corners. So those unit cells in which atoms are located only at the corners of the unit cell, they are known as primitive, and if atoms are located at some other positions along with the corners, then they are known as non-primitive. Done? आगे चलते. One more thing you see here, let us suppose there is an atom, this one is the atom. So this atom is participating in 4 unit cell, 1, 2, 3, 4, 1, 2, 3, 4. So in a cell its contribution is 1 by 4. It is 2D geometry. If you go for 3D, the cell will become cube. So this atom will participating in 8 cubes, 4 these front which you can watch and 4 from back side. So in a 3-dimensional case, each corner atom is participating in 8 unit cells. So its contribution is 1 by 8 in a cell. आगे चल करके जरूरत लगेगी, चलो फिर समझा दूंगा तब. Let us come back to the other point. Crystal coordinate system. Crystal coordinate system. Crystal coordinate system. Let us suppose this is your lattice. These are lattice point, and at each lattice point there can be an atom. So if you want to define a coordinate system in the crystal, how can you define? That we are wanting to discuss here. First of all, you have to select any unit cell. So select any unit cell, conventional unit cell you select. So let us suppose I am selecting this unit cell, right? We can have other choice also, we can have this unit cell as well. Let us suppose I am talking about this first. So if I choose this unit cell, then select any corner as origin, any corner. Out of these 4 corners, you can select any corner as origin point. Then the directions along the edges of the unit cell will define basis vectors. They are known as coordinate axis, right. So, suppose it is x direction and it is y direction. This angle is, let us suppose, gamma. So, the dimension of the unit cell along x axis, it is basis vector A, and the dimension of unit cell along y axis is known as basis vector B. So, A and B are vectors along the edges of the unit cell, vectors along the edges of the unit cell, along the edges of the unit cell, edges of the unit cell. These are known as basis vectors. Both of these are known as basis vectors, basis vectors. इनको हम लोग basis vector कहते हैं. Now you see, my dear friend, so you have defined a coordinate system O, X, Y. It is in 2D. If it is in 3D, then you will have O, X, Y, Z. Third direction will also come into the picture. Here this gamma angle is 90 degree, and if the gamma angle is 90 degree, then it will be known as Cartesian coordinate system. But it is not necessary that we will always have Cartesian. We can have non-Cartesian coordinate system also. Means the angle between the axis can be other than 90 degree. For example, here, if we select this point as origin, and if I select these lines, this and this as basis vector, so this is x, this is y, this angle is gamma. So, basis vector is this A and this is B. So, basically this is non-Cartesian coordinate system. This one is non-Cartesian coordinate system. So, you can have Cartesian or non-Cartesian coordinate system depending upon your choice of unit cell. So, first of all, you have to select a unit cell, and then according to the unit cell you can decide the coordinate system. Any corner of the unit cell can be taken as origin point, and then the vectors along the edges of the unit cell define the basis vectors or directions of the coordinate. So, you can write it, select a corner of the unit cell as the origin point, select a corner of the unit cell, corner of the unit cell as origin point, as origin point. Select a corner of the unit cell as origin point. The vectors from the corner, the vectors from the corner, vectors from the corner along the edges, the vectors from the corner along the edges of the unit cell, along the edges of the unit cell define basis vectors, define basis vectors like A and B. Please note down this. This is crystal coordinate system. It will entirely depend upon our choice of unit cell. Although we would be selecting always with the conventional unit cells, I will be talking about the conventional unit cell very soon. Done. आइए, next is lattice parameters. Lattice parameters. Since our material is 3-dimensional material, so unit cell will be a 3D geometry. Let us suppose this is our unit cell. This one is our unit cell. This is our unit cell. It's not necessary that it is cube, it can be any shape. Basis is just a vector along the direction, that is edge length along that direction. Unit cell की edge length उस direction में, उसे हम basis कह रहे हैं, and that is for both Cartesian as well as non-Cartesian, for both. Right. Let us suppose we define a coordinate system. This is our origin point. This point I am taking as origin, and we are defining a coordinate system like this. Let us suppose this is x-axis, this is y-axis, and this is z-axis. Now, unit cell dimension along the x-axis is a. An angle in front of a is represented as alpha. The angle between the y and z axis in front of a is represented as alpha. Now, the unit cell dimension along the y axis is known as b, and the angle between x and z in front of b is represented as beta. The dimension along the z axis is c, and the angle between x and y is known as gamma. So, we have three edges: a unit cell edge length along x axis, b unit cell edge length along y axis, c unit cell edge length along z axis. Alpha is interaxial angle. Interaxial means angle between two axes. Interaxial angle between B and C. Between B and C. Beta is interaxial angle. Interaxial angle between A and C. A and C. Gamma is interaxial angle between A and B. Now you have 6 parameters, and the interrelationship of these 6 parameters will define the shape of the unit cell. Let us suppose A is equal to B is equal to C, and alpha, beta, gamma all are 90 degree. Then the shape of the unit cell will be cube, and you would be saying it is a cubic unit cell, a cubic crystal structure. Similarly, let us suppose A is equal to B but does not equal to C. Alpha beta 90 degree but gamma is 120 degree. The geometrical shape will become a hexagon, and you will be saying that it is a hexagonal crystal structure. So the shape of the unit cell will be decided by 6 parameters, and those 6 parameters are 3 dimensions ABC and 3 angles alpha beta gamma. These 6 parameters are known as lattice parameters. These 6 parameters are known as lattice parameters. These 6 parameters, 3 edges of the unit cell and 3 interaxial angles are known as lattice parameters. Please note them down. Pratik, Cartesian coordinate system is that coordinate system in which all the directions are perpendicular to each other. And non-Cartesian coordinate system is that coordinate system in which it is not necessary that directions are 90 degree. Ankush, mechanical you have studied all this, so you can skip this part. Today's class you can skip. Even the next class also you can skip, because in mechanical you may have covered all the part of the crystallography. Except the last few things like defects, here we study certain defects which you do not study probably. Maybe studying that also except 1 or 2. So mechanical people can skip this class. I am happy to know it, Pratik. Right, let us go on. Now, based upon the interrelationship of these 6 parameters, we have different shape of the unit cell. So conventionally we have 7 types of unit cells, like cubic, orthorhombic, monoclinic, hexagonal, all that. After that things get repeated, so we consider only 7 types of conventional unit cells. In a particular unit cell, atomic arrangement can be in more than one ways. For example, let us suppose we have cubic unit cell. So in a cube you can have atoms only at the corners of the cube, that is one type. So that is known as simple cubic crystal structure. But suppose along with the corners you have one atom at the center of the cube, then it is known as body centered cubic crystal structure. Suppose along with the corners you have atoms at the face of each cube, then it is known as face centered cubic crystal structure. So what I am wanting to tell you, in a cubic crystal structure there are 3 types of atomic arrangement. So we can say that in cubic crystal system there are 3 space lattices. Lattices are basically those places where atoms can be arranged. So you have 3 space lattices. Similarly, in some of the coordinates, some of the crystal system you have 1 space lattice, in some of the crystal system you have 2 space lattice. So in total in all the 7 crystal systems you have 14 space lattices. So this set of 7 crystal system and 14 space lattices is known as Bravais lattices. So next heading is Bravais lattices. Bravais lattices. This contains 7 crystal systems. 7 crystal systems and 14 space lattices. We need not to know about each space lattice, but we must know about 7 crystal system. Because to form a particular geometry, ABC and alpha, beta, gamma must satisfy certain conditions. Like if A is equal to B is equal to C and alpha, beta 90 degree, then only cube can be formed. For any other combination of ABC and alpha, beta, gamma, cube cannot be formed. So in order to get cubic unit cell, this condition must be satisfied. So likewise, I am going to write 7 crystal systems, and for each crystal system, what should be the condition between ABC and alpha, beta, gamma, that you need to memorize. Because for cube all the dimensions are same, then it is same. You cannot have any logic. This is the condition, then only the cube will be formed. So you have to memorize for all these 7 crystal systems the relationship between ABC and alpha, beta, gamma. Right. So let us write these things: 7 crystal systems and the interrelationships. Crystal system. Conventional unit cell. Conventional unit cell. So let's see one by one. First, cubic crystal system. So cubic. In order to become cubic, A is equal to B is equal to C. Alpha is equal to beta is equal to gamma is equal to 90 degree. Next, tetragonal. Tetragonal. So it is A is equal to B does not equal to C. Alpha is equal to beta is equal to gamma is equal to 90 degree. Then the geometry which will form, that is known as tetragonal. Next, orthorhombic. Orthorhombic. Here A does not equal to B, does not equal to C. Alpha is equal to beta is equal to gamma is equal to 90 degree. This is the third. Fourth one is hexagonal. A is equal to B but does not equal to C. Alpha is equal to beta is equal to 90 but gamma is equal to 120 degree. Next is trigonal or rhombohedral. trigonal or rhombohedral. So for trigonal, A is equal to B is equal to C, A is equal to B is equal to C, alpha, beta, gamma all are equal but not 90 degree. Alpha, beta, gamma but not 90 degree. Next, monoclinic. Next is monoclinic. In monoclinic, A does not equal to B, does not equal to C. Alpha and gamma are 90, but beta does not equal to 90. And the last one is triclinic. The last one is triclinic. In triclinic, nothing is equal. A does not equal to B, does not equal to C. Alpha does not equal to beta, does not equal to gamma. Please have a look. You have to memorize these 7 crystal systems. They used to ask questions from here. Do it quickly. Trick बना लो बेटा रमन, you can make the trick. If you see, इनको प्रॉपर ऑर्डर में अरेंज करके बनाने की कोशिश करो. टॉप 3 एंगल्स सेम हैं. ऑर्थोरोम्बिक को नीचे लेकर के चले आओ तो ए बी सी 3 में अनइक्वल है. कुछ ऐसा बना सकते हो. Out of these 7 crystal systems, we are mainly interested in cubic one. So let us try to understand the cubic crystal system. Here we have to mainly concern with cubic crystal system. I know in cubic A is equal to B is equal to C, alpha, beta, gamma 90 degree. Shape of the unit cell is cubic. So cubic crystal structure. Next heading. Cubic crystal system. In a cubic crystal system, A is equal to B is equal to C. So you need to define only one edge length because all the edge length are same, and you need not to define angle. We know that to make a angle, to make a cube, angle must be 90 degree. Raghav is saying that we can say that most regular form is cube and irregular is triclinic. Yes, you can say that. Please watch it quickly. Someone said to show it. Please do it quickly. Please do it quickly. Done? Shall I go ahead? Workbook answer key Akhilesh available at my Telegram group. 2 days back someone shared it again, so you can refer it. Shall we go ahead? Let's see cubic crystal system. So in cubic crystal system there can be 3 types of space lattices. The first one is simple cubic crystal system. This kind of cubic crystal system is generally exhibited by manganese, polonium, fluorspar, etc. Manganese, polonium, fluorspar, etc. Here atoms are situated only at the corners of the cube. Here atoms are situated only at the corners of the cube. Actually atomic arrangement is like this. In crystallography we assume that atoms are hard and spherical body. So this assumption you have to take throughout the crystallography. So we are assuming that these atoms are hard and spherical. All of them are hard and spherical. So they are arranged in this way as I am making here. These are the atoms. You please assume them hard and spherical. Although I am unable to make them spherical, but you have to assume it. So they are arranged like this. It seems they are situated at the corners of an imaginary cube. It seems that they are situated at the corners of an imaginary cube, and that's why it is looking like cubic crystal structure. It seems that these atoms are situated at the corners of the cube. The distance between the centers of the adjacent corner atoms is edge length of cube, that is represented by A. So this is A, this is A. In all direction it would be same. This is A in that direction also. So we can make it something like this. Suppose this is a cube. right. So suppose one atom is at this location, one atom. These two atoms are touching each other. Just these two are the atoms which I am making here. Just it is a way to show them by reduced sphere. These are the corner atoms. So you have 8 corner atoms. You can make the front view like this. You make these 4 atoms as front view. This atom, this atom, this atom, and this atom. Connect these centers. Like this. Now, you see, this distance between two centers is A, atomic radius, and this is nothing but R. R is atomic radius and A is lattice parameter as length of the cube, atomic radius. This is A. Right. Please make it quickly. Make it quickly, then we have to discuss few things here. Telegram channel name is Anunad, A-N-U-N-A-A-D, Anunad 22. You search it, you will get it. Do it quickly. Now you see, we want to define few terms in order to see the performance of this unit cell. In order to define the properties of the unit cell, we are wanting to define few terms. So the first term is coordination number. The first term is coordination number. Let us first write the definition of coordination number. It is defined as the number of nearest and equidistant atoms. It is defined as the number of nearest and equidistant equidistant atoms with respect to any considered atom, with respect to any considered atom in a unit cell. It is defined as the number of nearest and equidistant atoms with respect to any considered atom in a unit cell. Not only in a unit cell, including all, in a crystal कह सकते हैं. So you simply write, it is defined as the number of nearest and equidistant atoms with respect to any considered atom, right. So any atom, if you take the reference atom, considered atom, let us suppose I am taking this atom. So if I take this atom, so what are the nearest members? One this, this, this and this. These four in the same plane. One would be out of the plane, this side, and one back side to the plane. So total there would be 6 atoms. In visualize this, let us suppose the room in which you are sitting, that is a cube. Let us assume it. And suppose that at each corner of the room there is one atom. Now consider any one corner as the reference and try to calculate nearest number of atoms. So let us suppose I am considering bottom corner, then one atom at this side, one atom at this side, one atom at back side, one atom at back side. So within the bottom plane you have 4 atoms, then one top of the plane and one below this atom. So how many atoms are there? 6. So consider any atom. Let us suppose I am considering this top corner as the reference atom. So in the top plane, one at this side, one at the back side, one at the back side, one at this side, 4, one below it, 5, and one above it, 6. So coordination number for simple cubic crystal system is 6. It is nothing but the number of nearest and equidistant. Equidistance means at the equal distance atoms. Second one, atomic radius, that is R. You see my dear friend, if you see this figure, then R and plus R, how much it is? 2R, 2R is equal to A. So we can write R plus R is equal to A. So 2R is equal to A. R is equal to A by 2. R is equal to A by 2. This is atomic radius. Now the third parameter which we have to calculate is effective number of atoms per unit cell. Effective number of atoms. Effective number of atoms per unit cell. Effective number of atoms per unit cell. This we are wanting to calculate. I am representing it by capital N. You can represent it by small capital N. Number of atoms per unit cell. Have a look here. This corner atom, this is participating in 8 cells. How? One cell this, one this, right? You go like this, you go like this, you go like this. 4 are visible and 4 are backside. So this one atom is participating in 8 cells. So if an atom is participating in 8 cells, how much it will contribute in one cell? 1 by 8. So each corner atom is contributing 1 by 8 in a cell. Corner atoms participate in 8 identical unit cells. 8 identical unit cells. Hence, they contribute. Hence, they contribute 1 by 8 in each unit cell. So n is 1 by 8 plus 1 by 8 plus up to 8 times, because there are 8 corners. So you can write it n is equal to 8 into 1 by 8, that is 1 atom per unit cell. This is 1 atom per unit cell. Effective number of atoms per unit cell. Last parameter which I want to define is atomic packing factor. Atomic packing factor, popularly known as APF, sometimes also known as atomic packing efficiency. Atomic packing efficiency. It is defined as, APF is defined as sum of atomic volume in a unit cell. Atomic volume in a unit cell divided by volume of a unit cell. Volume of a unit cell. Sum of atomic volume in its unit cell divided by volume of a unit cell. It comes out as APF is sum of atomic volume. There are n atoms. Effectively, the value of n will keep on varying for each type of unit cell, multiplied by volume of one atom. We are considering atom size is sphere, so volume is 4 by 3 pi r cube, and it is divided by volume of unit cell. Unit cell is cube, so volume is a cube. Now for simple cubic, if I calculate this value for simple cubic, APF is equal to, n is how much? 1, 4 by 3 pi, r we have calculated a by 2 ka whole cube, divided by a cube. So from this APF will come out as 0.52 या 52%. It means 52% volume of each cell is occupied by the atoms and remaining 48% volume is void. Yes, it is true. You see, if you see at this point here, so you have this atom, but this place is what? Void. This place is void, empty. This place is empty. So you have 48% empty space and 52% filled space. Please note down from here. Quickly do it. किसी को अभी क्रिस्टल पार्ट ही लिखना है, जल्दी करें। Yes, Akhilesh, we would be getting several things, like we would be calculating density with the help of these parameters. In the upcoming classes we would be doing that. So today I wanted to discuss only up to this point. Here onwards we will be discussing in tomorrow's class, and uh, uh, tomorrow this chapter will be probably completed, almost completed if not completed. We'll try to complete it by tomorrow. This is a very important chapter. You will be getting several questions in the examination, past examinations from this chapter. In the beginning of the class, I got a little bit furious because of the message of one person. I'm extremely sorry for that. I should have shown a mature behavior. He may not be mature like me, but I should have shown a little bit more matured behavior rather than being angry. So I'm apologetic for that. As a teacher, I should not have become a bit angry. As far as this decision is concerned, if it would have been manageable for me to manage in both of the languages, then I would have done it already. Because I am not interested to harm you in any way. My aim is not to make you dissatisfied. My aim is to teach you. My aim is to give you the best possible content, and so that you can understand each and everything in the better manner. But I am bound by the rules, and because of that it could not become manageable for me to continue in the language desired by you. And that was the reason I got a bit frustrated. I tried to convince, but it was not as per the expectation. And then the person, whosoever was he was trying to teach this way, that way, and that. So that triggered me, although it should not have triggered. So let's meet tomorrow and let's try to study the further topics. Those who are not happy, I will advise you, there are 10 topics in the paper 1. It's not, the paper 1 is not merely material science. Particularly Mr. Meena, if you are there, I would like to advise for you, because as you have made mood regarding me and regarding the class, so it will not be effective for you. You will not be able to gain anything from this class. So better you skip this subject. It's not wise to waste your time 10 days, 12 days in studying a subject which you are not able to follow. So those who are not able to follow because of any reason, I will advise them to skip the subject and focus on the other subject. There are 9 subjects. Ultimately, it doesn't matter whether you are in this class or not. Ultimately, the thing which matter is you should get selected. So be it Mr. Meena or be it any other student, if you are not able to follow the things and you cannot change it, I cannot change it, we both are bound by the certain limitations. So better is to find some solution. So I found solution to teach in the way as I have been told. You need to find the solution. If you are not able to grasp it, better leave it and try to focus your energy on any other subjects. Wish you all the best. Thank you. Have a wonderful time.